This video is about expanding irrational numbers using their decimal form into simple continued fractions. We'll discuss the process and work an example. Let's get started. Before we do anything at all, I'd like to mention one good thing and one bad thing about using decimal form. The good thing is it gives us a quick and easy way to get some terms of a simple continued fraction. The bad thing, though, is we have limited precision in decimal form, so we're always dealing with approximations. As a result, you can get errors if you aren't careful. Okay, let's discuss the process. It is similar to what we saw in this other video about using decimal form to expand rational numbers. It might help to watch that video if you haven't already. First, record the value of alpha. Since we are using decimals, it is easy to see the integer part denoted a and the fraction part denoted 1 over alpha sub k plus 1. Then subtract a from alpha so that now we have 1 over alpha sub k plus 1 isolated. Take the reciprocal, which gives us alpha sub k plus 1. This is all pretty easy to do with a calculator or a spreadsheet. The next step involves repeating the first three steps. If the number we are expanding is a quadratic irrational, repeat steps 1 through 3 until the remaining fraction, 1 over alpha sub k plus 1, is very close to a previous value. What do we mean by very close? It means the two values differ, but only by an amount that is due to imprecision of the device you're using. When this occurs, you can stop. The sequence of values of a, which make up the simple continued fraction, will start repeating with the value just after the one with that value of 1 over alpha sub k plus 1. We'll come back to the process, but let's do an example and see how this works. We'll expand the quadratic irrational number 20 plus the square root of 37 over 11 into a simple continued fraction. We'll use a table like we do in other videos. We have columns for the subscript k, a, and 1 over alpha sub k plus 1. A and 1 over alpha sub k plus 1 add up to alpha. A is the integer part of alpha, and 1 over alpha sub k plus 1 is the fraction part. After we fill this in, the values in this column, the column for the values of a, will have the simple continued fraction. To get started, let's find the decimal form of the number we're expanding. 20 plus the square root of 37, I have to the equals here, and then divide the result by 11. It is approximately 2.37116023. I say approximately because we can't put the exact value in decimal form. Anyway, this 2 is the integer part a, and everything after the decimal is approximately the fraction part, 1 over alpha sub k plus 1. We'll put this in the row for k equals 0. A is 2, and 1 over alpha sub k plus 1 is all of this. Subtract a from this, which isolates 1 over alpha sub k plus 1. Take the reciprocal, and this gives us the next alpha, alpha sub k plus 1, approximately. Record these values in the row for k equals 1. A happens to be 2 again, and 1 over alpha sub k plus 1 is all of this. As we complete each row, we have to keep an eye on this column. We want to notice if we get a value of 1 over alpha sub k plus 1 that is very close to a value we already had. This value is not very close to this one, so we keep going. Subtract a equals 2 and take the reciprocal. In the row for k equals 2, a equals 1 and 1 over alpha sub k plus 1 equals all of this. This value is not very close to either of these, so we keep going. Subtract the integer part a and take the reciprocal. In the row for k equals 3, a equals 2 and 1 over alpha sub k plus 1 equals all this. This value is not very close to any of these, so we keep going. Subtract 2, take the reciprocal. In the row for k equals 4, a equals 3 and 1 over alpha sub k plus 1 equals this. This time, though, the value of 1 over alpha sub k plus 1 is very close to this one. In fact, all the digits shown on the calculator are identical. The calculator maintains more digits than it shows, though, and way over to the right, there is a difference between these values. We'll say they are very close, so we can stop. A starts repeating in the row after this, so this one begins the repeating part. We can write the answer now. 20 plus the square root of 37 over 11 equals 2, 2, 1, 2, 3, with the 1, 2, 3 repeating. You can check this by calculating convergence of this simple continued fraction and confirming that they provide better and better approximations of the number we expanded. This gives us confidence we have the correct simple continued fraction. You can be completely sure, though. What you can do is recover the value of this simple continued fraction. If you get this number, then you can be sure that the approximations in the decimal form did not lead to an error. In the coming series of videos, we'll talk about recovering quadratic irrationals from their simple continued fractions. In one of those videos, we'll use this as an example. Let's get back to the process. What do you do for other irrational numbers? Their simple continued fractions are not periodic. They don't end with something that repeats indefinitely, so there isn't an obvious time to stop. You can do this and get some terms though. What you would do is repeat steps 1 through 3, and I'll say indefinitely because as long as you have sufficient precision, you can keep proceeding. But proceed with caution. Eventually you'll exceed the precision of your calculator and the terms will no longer be correct. Perhaps in some other video we can discuss this further, but the purpose here was just to show the basic steps. In this video we discussed the process for using the decimal form to expand irrational numbers and worked an example. That's all for now.